So about 58 million Americans in the United States rely on private wells for drinking water. That's roughly about 1 in 8 people. And unlike public water systems, private wells aren't regulated under the Safe Drinking Water Act, and there's really no routine monitoring required. So that means the responsibility for water quality lies on the well owner, and both in terms of testing and, most importantly, understanding the results. In many cases, we only know what's in the water if someone decides to test for it, and even then, testing is often limited to a relatively small list of contaminants, things like bacteria, nitrate, and a few common inorganic constituents. But as we'll talk about today, there's a growing number of contaminants that aren't typically included in standard testing, and that raises an important question about what we actually might be missing. So when we talk about emerging contaminants, we're not necessarily talking about things that are new. In many cases, these compounds have been used for years, if not decades. But we're only detecting them now more frequently in the environment. That's happening for a few reasons. Number one, us analytical chemists are doing a better job of measuring things. Analytical chemistry is always improving, and we can detect new things and things down to lower concentrations. We're also starting to recognize that the potential impacts weren't fully understood for many of these chemicals from before. At the same time, many of these contaminants are not currently regulated in drinking water, or they are beginning to just be considered from a regulatory standpoint. So what makes them really emerging is this gap. It's this gap between what is present in the environment, what we understand, and what we're actually measuring and managing. That's what makes them an emerging contaminant. And that gap becomes especially important when we think about contaminants and how they move through groundwater systems. So to understand why this matters to private wells, it's important to think about how contaminants actually move from the surface into groundwater. Private wells are strongly influenced by what's happening locally, not just in agricultural areas, but also areas like urban and industrial settings. Sources can include things like agriculture, septic systems, stormwater runoff, road salt, and even industrial contamination. And when water moves into the ground through the rainfall and recharge, it can carry these contaminants with it into the subsurface. Once these contaminants are transported with groundwater, moving through soils, fractures, and in some cases through pathways such as karst systems, very open, porous systems. Once their contaminants, and because private wells draw from a relatively shallow and local groundwater sources, they can potentially be sensitive to nearby inputs. So in many cases, the water quality of a private well is really the reflection of local land use and human activity. So the emerging contaminants that we were concerned about have a few key characteristics. First, they are mobile. They can move easily through subsystems, and they can be dissolved in water or even sometimes attached to particles. And in systems with rapid pathways, this mobility becomes especially important. Second, they're persistent, meaning that they don't break down quickly, they can remain in the groundwater for long periods of time, and they can travel long distances. And third, there are often detection gaps. We're not routinely monitoring for them, or the analytical methods are not there, are still being developed. And really the the combination of these three factors, mobility, persistence, and detection, is what makes emerging contaminants particularly relevant for private wells. And of course, there's other factors like occurrence and toxicity, which are also important. But it's also understanding this mobility, persistence, and detection that helps explain why we're finding them in groundwater at all. All this talk of water is making me thirsty.
Remember, you guys didn't buy beer.
That's right. All right. All right. Where are we at? I lost my place when I did that. I'm sorry. Am I ready? I'm really sorry about that. Oh, okay. So what are we actually finding in groundwater systems? And increasingly, it's a wide range of contaminants that aren't traditionally part of groundwater monitoring. For this talk, I'm going to focus on 4 broad categories that are particularly relevant for private wells. These include microplastics, pesticides, PFAS, and pharmaceuticals and personal care products, also known as PPCPs. That's a tough acronym to say. These are all very different types of contaminants. Some are particles, some are dissolved chemicals, but they often share those key characteristics that I talked about before. They can be mobile, they can be persistent, and in some cases, they're not monitored. These are just a few examples, yet there are many more that could potentially be present in a groundwater system, far more than what we normally measure. And I'll walk through each of these briefly with a few examples from current and past projects that have been going on at the Prairie Research Institute. I'll start with microplastics. I always got to start with plastic. And that's because this is one of the more unexpected contaminants that we're finding in groundwater systems. So I have to, by law, tell you that microplastics are small pieces of plastic less than 5 millimeter in size, and they are now very widespread across environmental systems. At the same time, plastic pollution is drastically increasing over the past several decades, contributing to their widespread presence. They've been documented in our oceans, in our waters, in our sediments, and our soils. But for the longest time, we thought that groundwater was protected from microplastics. The idea that soils and sediments could act as a natural filter protecting our aquifers from microplastics has been the common thought. But recent work suggests that this assumption doesn't always hold, especially in systems where water can move quickly. And that's just the particles themselves. As I spoke about earlier, many of these plastics contain additives and interact with other contaminants, which acts as another layer of concern. So the presence of microplastics in groundwater starts to challenge some of our basic assumptions about how these systems are protected. So to give you an example of how this applies to groundwater systems, we recently looked at microplastics in karst aquifers there in Illinois. Rough night. We collected samples from both springs and shallow wells across 2 different karst regions. It's important. What we found was that the microplastics were present in nearly all of the samples we looked at, 16 out of 17. And most of the things that we've detected, the shapes, were fibers. And that's important because fibers are typically associated with things like wastewater and septic systems. In a lot of my other studies, actually fragments are the most abundant types of shapes that we find. So taken together, these results suggest that microplastics can move from the surface into groundwater systems, likely through some kinds of pathways as we discussed earlier: fractures, conduits, and rapid recharge. But more broadly, it highlights the connectivity between the surface activities and the groundwater quality in these systems. And these findings didn't occur in isolation. Now, I'll stop for 1 second. In this photo here, does anybody notice something strange about this photo? We're looking at plastic, right? That's right. That was a sample for pharmaceuticals and personal care products. The next sample was a glass bottle. That was for microplastics. But people always give me crap about that photo, so I had to cover that. All right, so where are we? So in our study, we also looked at pharmaceuticals and personal care products. And again, I shouldn't have gotten off topic here. In our study, we observed microplastics tended to co-occur with other indicators of human activity, things like nutrients, chloride, and compounds such as triclosan, which is an antibacterial that's typically associated with personal care products. These are typically also associated with wastewater and septic influent. So, rather than being a standalone signal, microplastics appear to be part of a broader pattern of contaminants linked to human activity and human inputs. In fact, microplastics appear to be moving through groundwater systems along with human-derived contaminants. And as it reinforces the idea that groundwater systems, especially in vulnerable settings, are reacting to what's happening to the surface. And while microplastics are one example, they're just part of a broad group of emerging contaminants that we're just starting to realize about in groundwater systems. So with that, I want to get into another class of contaminants, and that's pesticides. They have been studied for a long time, but they are still evolving in very important ways. In agricultural areas, we are known for decades that compounds like nitrates, herbicides, and pesticides can move from the surface into the groundwater. This has been one of the most well-studied examples of how land use directly influences water quality. And this is especially relevant for private wells since they are located in rural settings where agricultural land is common and where wells may be relatively shallow or more vulnerable to local inputs. From a groundwater perspective, many of these compounds are mobile. They can dissolve readily in water and move to the subsurface, particularly in systems with rapid recharge and limited filtration. What's changing, though, is the type of compounds we are dealing with. In addition to legacy pesticides, we are now seeing newer compounds that are designed to be even more water soluble and even more mobile, so they can be taken up by plants more effectively. But that same mobility increases the potential for it to reach our groundwaters. There are hundreds of active pesticides and currently in use, and new ones are being developed every day to grow far more than what we can routinely monitor in groundwater systems. So while pesticides are not a new concern, they continue to evolve. So that makes them an important part of the emerging contaminant landscape. And one example of these pesticides that are of emerging concern are neonicotinoids. These are a new generation of insecticides that are now among the most widely used globally, and particularly in agriculture. They are often applied as seed treatments, and one of the key characteristics is that they're highly water soluble, which allows them to move through the plant system and provide systemic protection. But that same property, again, high water solubility, makes them highly mobile in the environment. Many of the people I've known that done these studies have actually had nearly an impossible time finding seed that wasn't soaked in neonicotinoids. So as a result, these things have the potential to move through leaching and infiltration, and we're seeing increasing evidence of that. For instance, in Wisconsin, there was a recent study that found 78% of the wells sampled had hits for neonicotinoids. Now that is a specific agricultural setting, but it highlights the common that these compounds are finding their way into vulnerable groundwater systems. And importantly, neonicotinoids are just one example. There are many pesticide compounds, both existing and newly developed, and are part of the broader and evolving group of emerging contaminants. Quite honestly, I don't think pesticides are getting the attention that they deserve. PFAS. All right. Another important class by law I have to talk about is PFAS, right? Per and polyfluoroalkylated substances. They are a large group of synthetic chemicals that have been used widely for decades in industrial processes and consumer products. They have been used in non-stick coatings, stain-resistant materials, firefighting foams, and so on. One important thing to recognize, though, that PFAS isn't just one compound. It's a large class of compounds, thousands of compounds, extremely diverse, and that's what makes it more complicated. What makes PFAS particularly important from a groundwater perspective is the persistence. These compounds are often referred to as forever chemicals. Again, by law, I have to say forever chemicals when you say PFAS. That's because they readily don't break down. Once they enter our groundwater systems, they remain there for a long time, they can travel significant distances from the original source. And because of persistence, PFAS contamination is often widespread and long-lasting, even after the source has been removed. So they now have been detected in groundwater, surface water, and even drinking water supplies across the United States and globally. So while neonicotinoids highlight the role of mobility, PFAS highlights the role of persistence, and both are critical when we think about emerging contaminants in groundwater systems. Another challenge with PFAS is testing. We've been hearing that over and over, and I think we will hear that again this afternoon. But traditional PFAS analysis typically requires very specific and sophisticated and expensive laboratory instrumentation, and it can be both expensive and time-consuming. That creates a gap, especially for private well users and owners, where routine monitoring may not even be readily accessible. So a project that we are working on at the Prairie Research Institute in collaboration with Washington University in St. Louis is called the Trusted Tap Project, which I will give a lightning talk about this afternoon, and that'll be the last time you'll be forced to listen to me. This project is funded by the National Science Foundation, or the NSF. The goal of this project is to develop point-of-use filtration approaches for measuring PFAS by bringing testing closer to where people are actually using it, their tap, rather than relying solely on a centralized laboratory for analysis. This has important implications for private well users who often don't have easy access to PFAS testing or know when testing is needed. In many cases, private well users are making decisions with little information, and this approach can help close that gap. So efforts like this are aimed at improving access to water quality information, reducing barriers to testing, and helping communicating better for private well users. The last group that I want to focus on is pharmaceuticals and personal care products. These include a large range of contaminants, things like medications, antibiotics, and everyday products that people are putting down the drain. One important thing to recognize is the very diverse class of these with a wide range of uses and properties. What makes this different than the previous contaminants are the pathways to the environment. Rather than coming from agricultural and industrial sources, the compounds are getting into the groundwater through human use, entering water systems through wastewater and septic systems. This is particularly relevant for private wells, which also many homes rely on on-site septic systems, which can be a source of these contaminations to the subsurface. Also, many of these compounds are designed to be biologically active, and that's the reason they're used, right? Many of them are not also removed during treatment or natural filtration. So even though they are typically detected at low concentrations, there's a growing concern due to long-term and chronic exposure. So in our earlier microplastics work, we also saw a co-occurrence of compounds like this, including triclosan, which is commonly associated with personal care products. So PPCPs represent a different pathway into groundwater, one that is closely related to human activity. So stepping back and looking across these different classes of contaminants, microplastics, pesticides, PFASs, and PPCPs, we see very different sources and pathways, but they all share a common theme. First, many of these contaminants are mobile. Second, many are persistent. And third, there are many important detection gaps. So, while these contaminants differ in chemical properties, they tend to share these underlying characteristics, and that's really the combination that makes them important from a groundwater perspective. So what does this mean for private wells? The takeaway is that water quality is often more complex, more variable than we might assume. Unlike public water systems, private wells typically rely on limited, infrequent testing, and they often, even when we are testing, we may not be capturing the full picture. Many of these contaminants we talked about today are not the part of the standard testing panel. So in many cases, private well users are making decisions with incomplete information about their water quality. And that highlights the importance of improving both monitoring and access to information so that people can understand what's in their water and what it means. So to wrap it up, emerging contaminants are not just a future concern. They're already here and already part of our groundwater systems. We're seeing a wide range of compounds, from microplastics to pesticides to PPCPs, but they all share that common characteristic: mobility, persistence, and gaps in monitorings. So as we discussed, the challenge isn't about what's in the water, it's what we don't fully understand and what we don't fully measure. And this is an area where science is continuing to evolve. We improve our ability to detect and understand these contaminants, our picture of groundwater quality will continue to change. So for private well users, that also means staying informed about water quality, considering periodic testing beyond the standard panel, and taking advantage of all the new tools and resources as they become available. So improving monitoring, expanding access to testing, and continuing research will be essential moving forward. Thank you. No questions?
Do you want me to read your questions, or do you want to read your questions? It's up to you.
Oh, studies showing microplastic in bottled water. Yeah, a lot of that work's been done some time ago by, what was her name? Sherry Mason. She did a lot of studies of microplastics in bottled water. And yeah, just incredibly high numbers. But we know it's a major source. You get a lot more microplastics from drinking bottled water than you do in tap water or even private wells. It's a major, major problem. So I think I covered that one. We know for sure about microplastics. And reverse osmosis or removing any of these contaminants. Yeah, reverse osmosis does remove a lot of these contaminants, but again, it's very costly, right? And it needs to be maintained. Uses a lot of energy, but RO does remove most of these things. Let's see, how much PFAS is attributed from firefighting? Yeah, a lot of it, and that makes sense, right? Because we've directly applied this to the environment. So yeah, firefighting foams is a major source of these things, and they tend to stick around for decades after training activities or fire events where they've been used. Also, there's a lot of occurrences of fire suppression systems automatically just kicking them out on accident, like malfunctions. So that's a major source. Is it always one? Wait, is it always one of the three sources measured, but is it a prevalent source? Yeah, it is a prevalent source, definitely. Biosolids, too, is a major source of PFAS to the environment, biosolid applications. Those are the two largest ones in my mind. Food packaging also has an incredible amount, and that's one that I don't think it gets the attention that it deserves. Do you know if any of these current UM6? Yes, microplastics is on, microplastics is on CCL6. I don't know if it's on UCMR6, but I know it's on the EPA's radar. And so is pharmaceuticals, which is going to be a nightmare. I mean, that's just such a wide range of contaminants that, that's going to be a tough one. But I don't know what's on the UCMR6 yet. Does anybody know? Yet? Has it even been released yet? It has? Yeah, I haven't looked at it yet. I've been too busy preparing talks for this presentation. So. With the recent removal of some PFAS, yeah, the evolving regulations. Oh boy, here we go. EPA regulations. How could this impact?
It hasn't been removed yet, just so we're clear.
Yeah, well, first of all, I'm sorry, what was that? That's why I bring him with me. But the other thing about the PFAS regulations is that's not for private wells, remember. Private wells aren't regulated. Oh, here we got an argument. All right, let's go on to the next one. Is the trusted tap available to, not yet, but the goal is that, I'm glad that you asked that. So the Trusted Tap project is in its infancy, but we're actually working through what's called the Technology Accelerator, and we were supposed to bring that into a business in the next 3 years. So again, we're working very hard to turn that from a proof of concept into a viable business in the next 3 years. So hopefully it will be open nationally in the near future, which is 3 years is a really fast time. Are microplastics more in certain soil types? Yeah, definitely karsts. I'm going to tell you, karst systems have high potential to have microplastics in them. Deep aquifers, I wouldn't expect to have as much. I found a study from the University of, you changed it on me. Since PFAS, thank you, Steve. You know what, I need my glasses. I just realized, why does it look so blurry? Cloud condensate. Yeah, I read that one too. Are you familiar with the study, and what are your thoughts about making this part of the water cycle? Yeah, small enough will get carried in cloud condensate. In fact, I've looked at microplastics in rainwater, and I got some interesting results, but I didn't want to publish it because of the way the samples were collected. They weren't collected thinking about microplastics, so I was always worried about contamination. But USGS did publish something similar to that, and it's definitely can be part of the water cycle. So yeah. Next one, please, Jesse. How many more? Oh, that's right. I'm sorry. Since PFAS is long-lasting, even after contaminant has been removed, it's the effect's the same to private wells, and there's a routine. And is there a routine that needs to be adapted as well as a well owner to maintain wells? Well, yeah, definitely. Even after you remove the source, you need to keep testing, right? And it will definitely be around for a long time. So is there a routine that needs to be adapted as well as a well owner to maintain water quality. Yeah, I think there would be a need to keep testing and keep checking it to make sure that even after the source has been removed, that it's out of the system. But that's another problem, is we need a cheaper, faster, quicker way for PFAS analysis. And that's something my lab's been working on as well, is a screening method. You mentioned biosolid slug application of PFAS. Can you address the scope of this problem? It's pretty large, and it's a major problem for the utilities. So if they're getting ready to be regulated for PFAS and biosolids, but what else are you going to do with them, right? If you don't land apply biosolids, you're going to put them in the landfill. When you put them in the landfill, that PFAS is going to translate to the landfill leachate and go right back to the wastewater treatment plant, and we're just going to keep shuffling it back and forth, right? So that's how we deal with environmental contaminants, right? We just move them to the least objectable environmental component, and we usually don't treat them. So that's a struggle. That's definitely a struggle. And that's something that people are definitely trying to wrap their heads around right now. I hope I cover that one. For PPCPs, particularly for personal care products and household soaps, what is the long-term solution for these everyday usage items entering groundwater? Yeah, that's a tough question too. I mean, yeah, just try to limit the use of these things and catching them before they get out to the environment. The further that we can treat these things upstream, the better, right? I mean, I've seen a lot of people develop these wonderful materials, and the intended use is to take it to the wastewater treatment plant and treat the effluent or but I think that we need to do these things further upstream. Like, I think about ways that, can we treat pharmaceuticals at the toilet? Can I develop a material that I put in the toilet that captures those pharmaceuticals before they get to the wastewater treatment plant? Because I think that's a much more efficient way. It's the pollution prevention way, actually. So I do think about a lot of those things all the time. I always think about toilets, right? That's what they taught me in the lunchroom. All right, for PVC wells, PVC, this is going to be good. Okay, so for PVC and PEX plumbing poses significant. I am working on a study right now. In fact, I'm reviewing the report where we're looking at PVC shedding and plastic pipe. And it doesn't look like it's too much, but a lot of that has to do with the conditions of the pipe, how old the pipe is, and also the water conditions, because like in a treatment plant, they're disinfecting the water. So we've been doing these experiments where we're pumping simulated disinfected water through PVC pipes and looking at the shedding of micro and nanoplastics. And there is a little bit, but I don't think it's really that much of a concern, at least with the materials that I've looked at thus far. But I still got to review the report. Thank you.